Good evening, everybody. Thank you so much for coming tonight. And thank you both to Cleveland State University and specifically to Colette and to Jordan for the wonderful introductions. Tonight, I want to talk to you about stories, and stories of the stars and stories in science. Now, I don't know about you, but when I was little, I loved Greek myths. And specifically, I had this book, and I read it again and again and again. And I think that's pretty common. I mean, why wouldn't you love Greek myths? They're full of wonderful stories. Those stories are not just about the supernatural, but they're also about things that are very human. And they tell us not only about humanity and human nature, but also nature itself. They tell us how it works, how it's ordered, and our place in it. Now, the heroes and villains in Greek mythology lived in all aspects of nature. They were under the ground, they were in the oceans, and most especially, they were in the sky. Now, I'm guessing that here we don't have any ancient Greeks. However, you are probably familiar with some of these constellations, these villains and heroes of Greek mythology, because of the zodiac. So these characters are those that are most familiar to you, and even if you don't know all that much about Greek mythology or you never liked it as a child, you might be somebody who would pick out some of these constellations from the back of your newspaper and read your horoscope perhaps. So reading your story in the stars, I guess. Now, for astronomers, we use constellations kind of to describe regions in space or in the sky. So much the way that there are state maps that the borders of which tell us about regions of land and the cities within those exist within those states, constellations are very similar in that their boundaries describe a region in the sky, and then the stars within them are the cities within that state. Now, the zodiac constellations are located on the path of the sky that the sun moves through over the course of the year. And so they get a lot of attention. But there are actually quite a number of constellations, as you can see here. And in this historical map, you might see some that are familiar and some that are maybe not so familiar. So these days, there are 88 constellations in total. And while the zodiac gets all that attention, these constellations help us navigate the sky when we speak about it. Now, the number of constellations has changed over time, and that's because the practice of looking at the night sky and picking out patterns is very common, but the agreed upon constellations differ not only over time, but between cultures. And so when we think about constellations, we're very much used to thinking about this narrative where people are lying in a field, and in ancient days, there's no TV, there's no internet, there's no social media. Kind of sounds great, actually. Visit your local national park. So we don't have any of those entertainment things. So we think about constellations as being something that people looked at and told each other stories with. Now, practically speaking, today we use these to navigate the sky, and even though they just tell us these regions in space, even we astronomers have our particular favorites. And these are two of mine here. These are the constellations of Cygnus and Lyra. Cygnus is the swan, and Lyra is the harp. Now, I particularly love these two constellations because a patch just between them has given me a lot of work to do for the past several years. So located between the constellations of Cygnus and Lyra, on a patch of the sky just about as big as your palm, held out at arm's length, that's the patch of sky that we know of most of the planets that orbit other stars. And that's no accident. This was the region of the sky that the Kepler mission, a space telescope designed to find planets around other stars, studied over the main portion of its mission. And so most of what we know about these planets comes from this one patch of the sky. And I'll add that because we're in summer now, this is up in the northern hemisphere in the middle of the night and summer, so you can go out and see it too. You can usually pick it out even in city lights. Now, it's very tempting to think of these constellations as being solely for entertainment. But one of the things that I'll talk about tonight is that these were very commonly used ways of ordering the world around us. And indeed, constellations that we know of now that we most commonly refer to are the Greek and Roman constellations. But across different cultures, constellations were different. So while some names might sound sort of familiar, for example, in this image you're seeing the constellation of Virgo and also of Draco, other things might look a little different. So, for example, you might have heard of Orion, but you might not know that the constellation of Orion actually lies in the Baler, or the net, of Makali'i, the Hawaiian god. You might look at the celestial sphere from Pakistan and see some things that look familiar, and also some things that look rather different. And in fact, if we go to certain cultures, we might find that the stars are connected in ways that are completely unfamiliar to us, such as with this rubbing that was taken from a carving during the Ming Dynasty. And so we can find these common themes and also these unfamiliar themes, but we find that this is a very, very common practice in cultures throughout time. Now, because all of these different cultures were really looking at the same sky, and because a lot of this was naked eye observing, people were looking at the same stars. And so any of the stars that you see in the night sky, even if you're in somewhere that's a very dark location, you can see lots of them, they usually have more than one name. And in fact, they usually have lots and lots of different names. So when you look up at the night sky, you're seeing things that are commonly shared across cultures, but called by different things. Now, some of the themes that are in these myths around constellations are actually surprisingly similar, even when the cultures are very different, either spread across very large ranges in geography or very long periods of time. So what I'm showing you here are two constellations, Orion and Scorpius. So that's Orion up here on the left and Scorpius on the right. Now, in Greek mythology, the scorpion was created to attack Orion. The earth gave forth the scorpion. And so it makes a lot of sense when you look at these constellations because they're actually on opposite sides of the sky. And so when the scorpion rises, it's Orion that sets and falls. But surprisingly, Scorpio and Orion actually feature pretty prominently, if not as their scorpion and hunter mythologies, in other cultures as well. So for example, in Chinese mythology, the stars that were in Orion and Scorpius were actually associated with two brothers, a brother named Yanbo and a brother named Xishan. And these two brothers fought and fought and fought. They hated each other. And so they were given the job of taking care of these two patches of the sky and attending to these stars that were as far apart from each other as possible, which if you've ever moved away from a family member, maybe you can figure out why. But it's interesting that the patterns that were seen in the sky actually informed some of these myths. And so even very different cultures had things in common. And so we see that even across wide ranges in geography and also wide ranges in time, that while it might be the names of the Greek constellations that we know and the names of certain stars, the knowledge that has been created about the night sky is the product of cross-pollination between a very, very wide range in cultures, even sometimes separated by centuries or even millennia, as the case with these two extremely similar drawings of these constellations here. Now, I mentioned earlier that when we talk about constellations, a lot of times we think of this as being a kind of entertainment. And that makes sense for the modern culture that we share today in this room. And that's because when we think about going stargazing, or when we flip to the back of the newspaper and look up our horoscope, I know some of you have done it, we're looking for entertainment, right? This is something that we do in our spare time. It's not something that we necessarily do every day for most of us. And so while it's tempting to think of these constellations in their original form as being something to fill the time, they actually were quite functional. One of the things that's really interesting about constellations is that if you think about them, they were based on very careful observations of the night sky. They weren't merely for entertainment. They were based on calculations and observations that were incredibly important to the cultures that came up with them. They taught people when to plant, they kept the passage of time, and they represented the cyclical nature of life and death. It doesn't get much more serious than that. And what's more than that is that they represented the fact that you could take observations of the natural world and create structure from them. That you could take observations, watch the sky, and look for the cosmology that lurked in the chaos. And from that comes the idea that the universe is not just something that we are existing in, but it's something that can be observed and measured, calculated, and understood by humans, which is incredible if you think about it. And so today, as modern astronomers, we use this very same premise. It's in fact the premise that all of science is based on, that we can look at the world around us and make sense of it. And so nowadays, we have a little bit of a harder job because the things that we want to see are actually typically very difficult to see, at least with the naked eye. And so nowadays, we have telescopes to serve as our eyes on the universe. So the animation that I'm showing you here is from NASA's Kepler mission, a discovery of a planet that orbits around a star about 1,000 light years away. And this planet is known as Kepler 186f. Now, even back in many ancient cultures, people wondered about whether there might be planets out there that were similar to Earth, planets that orbited other stars beyond our sun. But it's an amazing thing that we exist in a time when we can actually start to answer this question definitively of whether there are Earths beyond our own solar system using science. And one of the reasons that we can do this is that we have new telescopes that are dedicated to this task. Now, before the launch of the Kepler mission in 2009, nobody could tell you whether there were any planets that were small around the size of Earth around other stars. We'd known for about 2 decades that there were other planets out there, but we hadn't found any that could potentially be like Earth. And that all changed because of the telescope that you see behind me here, NASA's Kepler mission. Now, Kepler is a very simple telescope. It really just collects light and tries to figure out whether planets the size of Earth are common or rare in the universe. And it does this by helping us see what can't be seen. Now, inconveniently, even for a nice telescope like Kepler, the kind of thing that we want to see when we look for planets around other stars still eludes us. What I'm showing you in the upper right there is a picture of Venus going in front of the sun. And in our solar system, we can see the surface of our star and we can watch that happen. Unfortunately, most planets are billions of times fainter than their star, and all of those stars are so far away that even with our best telescopes, they look like tiny little points of light. And so that means that instead of watching the nice high-definition version, what we instead do is use telescopes like Kepler to measure how bright the star is and watch for the tiny shadow of the planet going in front of its parent star as it orbits around again and again and again. And this means that if we make very careful measurements of that change in brightness, that we can find very tiny planets, planets whose shadows are very small. And to give you some sense of this, if you were an alien astronomer and you existed on another planet and you were looking back at the Earth and trying to figure out if there was a planet around our star, this would be equivalent to trying to see whether a fly had gone in front of a car headlight about a football field away from you. Pretty tough job. So these tiny little dips in the light are really what has told us that, in fact, not only are there other planets the size of Earth out there, but they happen to be some of the most common things that the universe makes. And this is really amazing because before 2009, no one could tell you the answer to this. And what this means is that there are a lot of places that we could potentially look that might host life beyond our own solar system. Unfortunately, it doesn't yet mean that we've found life, but stay tuned. We're hopeful. So that means that just in the past few years, we've gone from this orrery here being a model, a mechanical model of our own solar system, being the only thing that really mattered, to what we now call the Kepler orrery, where we have literally thousands and thousands of worlds around other stars. And the amazing thing is that this is really done with a very simple method. It's just the passage of a planet in front of that star, making it a little bit fainter for a few hours once every time the planet goes around. And what that means is that we can derive certain things about that planetary system. Now, we can't see it, but we can tell you how big the planet is based on how much light it blocks. And that gives us the planet's size, so we can compare it to the planets within our own solar system, decide whether it's big or small, likely to be large and gaseous or small and rocky. And we can also figure out the distance away it is from its parent star. And that's very important because it helps us understand how much light it's getting from its star, and therefore how warm it's likely to be, or how cold. And we look always for worlds that might host liquid water. And that's really an Earth bias thing. So it's not that there isn't life in the deserts too. It's just that we find that liquid water helps along the chemistry that we associate with life, and we find that it thrives in those environments. And so Earth is currently our only inhabited known planet, and so we go with our best guess. So how do we get from these thousands and thousands of worlds, where we just know the size of the planetary system and the orbits that the planets have, to something like this? So this is an artist's conception of a recently discovered system of planets called TRAPPIST-1. And this artist's conception is amazingly brilliant and detailed and beautiful. There you are on the ocean. You're seeing ice floating out in front of you. There's a very small red star at the center of this system. And so you see its orangish glow in the sky. And if you look carefully, you'll also notice that you can see the other planets of this system in the sky as crescents. And this is beautiful, but you might ask, how did we get to here from the size of the planet and how far it is away from its star? Well, the answer is that just as people took the observations of the planets and their motion and the stars and their motion over the night sky in the times that myths were being developed, we use storytelling to fill in the blanks. Now, this storytelling is informed by data or observations about the night sky and these particular planets, but it helps us understand whether these places might be the kinds of places that we would want to search for life in the universe. Now, you might wonder what it means to really say whether a planet is like Earth or not. Now, remember that we don't have that beautiful artist's conception. We only have size, and we only have how much light it gets. So imagine again that you're an alien astronomer, and you're looking at these three planets within our own solar system: Earth, Venus, and Mars. Now, these three planets are actually very similar in size. Earth and Venus are almost exactly the same size, and Mars is a little bit smaller. And if you were to look at them with your alien version of Kepler, you would say that Mars is a little bit further away from the sun, so probably a little bit cooler, and Venus is a little bit closer, so you might guess it's a little warmer, sitting closer to its sun. But the thing is that you, as the alien astronomer, having only size and distance, would never guess that Venus is hundreds and hundreds of degrees on its surface. There's a reason that you don't hear about Venus rovers. It would be more or less like taking your iPhone and putting it in a pottery kiln. And the reason for that is that Venus has this very, very thick atmosphere. We can tell its size, but if we were far away, we wouldn't know what its atmosphere is made up of. And so this thick atmosphere creates a very strong greenhouse effect that traps all of the energy from the sun and creates a very hot environment. Similarly, if you were an alien observer looking at Mars, you would say, well, it's a little further away, maybe it's a little cooler, and it's a little bit smaller, but sure, maybe given the right atmosphere, it would be warm enough to host life. Now, when we look at actual Mars's conditions today, we see that Mars is very, very cold. It has a very thin atmosphere, mostly made of carbon dioxide, which we can't breathe. And so it's not the kind of place that we would think of as being habitable or Earth-like. However, we also know from sending rovers there that it probably was in the past. Maybe not inhabited, but it once had standing water on its surface. And that's a very tantalizing hint that planetary natures can change over time. And this is detail that we miss when we look with our eyes in space, telescopes like Kepler. And this is especially true when we go to look out at planets that orbit around stars that are very different from our sun. So this is an animation of the TRAPPIST-1 system. This is a system of 7 planets that were discovered around a very, very tiny red star. A star so small it's almost closer to being the size of a large planet than anything else, which emits only fractions of a percent of the energy that our sun does. And the TRAPPIST-1 system actually might be more typical of planetary systems than stars like our sun with planets like Earth. And that's because these little red stars are much more common. So how are we, as the only currently known inhabited planet that orbits a yellow star relatively far away, a nice, comfortable 94 million miles or so, how are we supposed to know what the conditions might be like on these planets or on these little red stars? These stars give off most of their light out in the infrared portion of the spectrum, where we would interpret it as heat. We wouldn't even be able to see it with our eyes. And they're very, very cool. And so all of these planets are very close to their star. And that's why in that artist's conception, you could see them as crescents in the sky. And the truth is that we don't really know what these are like. And so we use what we have to fill in the blanks with scientific storytelling. Now, the interesting thing about this is that this scientific storytelling that's informed by data, it not only helps us create these beautiful artist conceptions, it not only makes these beautiful, evocative pictures, it also helps us understand what the conditions on the planet might be like in a way that can inform the kinds of experiments or observations that we might want to carry out, especially when the worlds that we're finding might be very, very different from our own planet. And so we take into account all of the lessons that we can learn from the planets and other bodies of our solar system to understand what it means to be a habitable or even potentially habitable planet, a place that life might form, grow, and thrive. For example, well, the observations of planets are mostly the observations of stars. It's that starlight that we're actually seeing, not the planet itself, at least in most cases. And that means that we can study what the star itself is doing to the planet. Similarly, we get the distance away from the star, and that means that we can study the planet's orbit. And that can help us understand not only how much starlight it receives, but whether other effects of gravity are at work. For example, I'm showing here Io, which is a moon of Jupiter, who in gravitational field from Jupiter is actually needed and creates a very hot interior. So it's the most volcanically active place in our solar system. Naturally, we want to look for water. And that's a trickier thing to do. Right now, we look for planets that might be the right temperature. But in the future, we might even be able to detect that glint that you see there, the little point of light off the surface of an ocean. And we've done this with space telescopes looking back at Earth. Really an amazing trick. We also want to know about ice, because ice here on Earth is very reflective. We think of it as being very bright, that you can go snowblind from being around too much of that bright, white, icy stuff. But it actually responds differently in the presence of some of this very red light, where it can become dark and absorbent. And so it changes the climate overall. And we also want to know about clouds. And so the habitability of a planet is not just about its size and how much light it gets. It also is about all of these other factors as well. And we need to understand them. And before we can observe them, although we will be able to do this in the future with some of the technology that's coming online, not just in the next couple of years, but in the very near future. In the meantime, what we do is tell ourselves stories about the worlds of our own solar system and how we might see them out in these other planetary systems. And so I'm putting up here this wonderful quote from my colleague Jason Wright, who's an astronomer at Penn State. And indeed, Carl Sagan actually said something somewhat similar, that we conceive of these planets as places. So what we're doing when we take this data, that's just a measurement of brightness over time, is we create a story that's informed by the things that we can observe close to home, just in the way that myths are the observations of human nature and nature itself placed into a larger context and story. Now, I think one of the interesting things about this is that the stories that we tell ourselves are really about not just the planets, but they're about who we see ourselves as well. And that's because when we say that we can imagine these planets as places, what we're really saying is that we can imagine ourselves there. Everything that we take a picture of in space is a place. It all has a physical location. But why do these seem so evocative? Why do planets around other stars have such a hold on the imagination? It's because we imagine ourselves going there. And we have, over long periods of time, a long history of science fiction and movies that show us what it might be like to live out in space. But the fact of the matter is that these worlds are not only unseen, but they're also at the moment unseeable, and they're impossible at the moment to visit. That might change one day, and I think it would be very cool if it did. But at the moment, we're kind of stuck with the planets that are in our solar system at the very least. Maybe one day we'll get to actually leave the solar system itself and go to some of these planets around other stars. But in the meantime, it's all storytelling. And that brings me to the point that I wanted to make about how we see ourselves in the context of storytelling. Because I think as we've talked about finding these planets around other stars, one of the things that we're saying is that we can see ourselves there, and that these stories that we tell ourselves are scientifically powerful. They're something that not only makes it relatable to us, of course, and makes for a nice press release with a beautiful graphic, but there's something that helps us understand the data that we take. So can I quickly see who saw this movie, Hidden Figures? All right, a lot of people saw it. I hope you liked it. I really loved it. If you haven't seen it, I won't spoil it for you, but I will say that you should, because it's really wonderful. So Hidden Figures, just to quickly summarize, is the story of 3 women who worked at NASA during the Apollo era, so in the 1960s. And these 3 women, and many like them, worked at NASA making contributions to the space program. And in particular, these women, Mary Jackson, Katherine Johnson, and Dorothy Vaughan, made essential contributions to the calculations, the engineering, and the computations that allowed us to go and put human beings in space. And in fact, there would have been no moon landing without these women's contributions. However, up until the time that the book that preceded Hidden Figures, and in fact the movie, came out, most people didn't know the names of these women. They didn't know that they were 3 out of many, many women, mostly black women in the computational department, who were making the calculations that sent humankind to the moon. Close your eyes for a moment and imagine who you think works at NASA. And that's important, right? Because when I say, who is a scientist? Imagine an engineer. Imagine a computer scientist. You might think of folks like these. This is Paul Allen, Bill Gates in their younger days. Yes, computers used to look like that. So you might imagine them, and this is not to diminish their accomplishments at all, but you wouldn't necessarily know the names of Katherine Johnson and Dorothy Vaughan and Mary Jackson. And there are other names that you might not know as well. Grace Hopper, for example. And these women contributed to the foundations of computer science and engineering and aerospace in general. And yet their stories go untold. And there are countless examples like this. If I say, who's an inventor? You might think of Thomas Edison. But I bet you don't think of Hedy Lamarr, who is better known for her film career, but actually invented some of the technology that makes GPS and wireless possible. And I bet you don't know Lewis Latimer, whose filaments he invented made Edison's light bulbs work to begin with. Similarly, if you think of who an astronomer is, and even I get this today, people tell me all the time, oh, you don't look like an astronomer. By definition, I look like an astronomer. But if you, and I did this test last night, you can try it at home, see if your Google search algorithm works a little differently. But if you Google famous Harvard astronomer, you get this guy. This is Edward Pickering. However, these women at the upper right are the Harvard computers. This is who did Pickering's math. And several of them made huge contributions to astronomy in general, going on to now be recognized for their contributions to the understanding of stars in the context of this lab. But this was because, much like in the 60s at NASA, this was women's work, doing these calculations that put humanity on the moon. And yet, we don't hear those stories. And similarly, today, Harvard is the site of a training program for young astronomers that is named for this gentleman, Benjamin Banneker, the first black astronomer in the United States, who, at the time of slavery, was making astute observations and calculations of the night sky. So all of these stories that we tell serve an essential role, because while it doesn't necessarily matter whether somebody is a famous scientist per se, fame doesn't really have to do with whether you're good at science or not. But what it does do is capture the imagination of who a scientist is and who can see themselves as a scientist. And so when we look at these so-called famous examples of science, and this is, by the way, a screen capture of me just scrolling through everyone who Google thinks is a famous scientist. When we think about these faces, the future generation looks to who we think of as a scientist and tries to see themselves there, in the same way as we have always looked to our observations of nature and tried to see ourselves amongst the stars and our place within the universe. And so when we have these stories that go untold and unseen, we limit the ideas of who creates knowledge. And that's the thing, is that all of these myths that we've talked about and the knowledge that has been created today that comprises modern astronomy and also ancient astronomy was contributed to by multiple cultures over time. And some of those stories we know, and some of them they don't. You don't know. And the fact of the matter is that all of the future knowledge we have, we co-create together. And we can't afford to limit the idea of who can be the creators of knowledge, because this is a very complicated universe, and we need everybody to lend a hand. So what the constellations tell us is that we should not only take part in observing the incredible night sky, in looking out at the constellations such as Orion that you see there, and understanding them in the context of our universe and how it's structured today. But we should try to learn some of the unknown names, the names that we don't know of these stars, the origins of those names, the other ways in which people have seen the sky. Because together we are the co-creators of the knowledge that we have around the universe. And we can learn great things from these myths about ourselves and our reality that we have today. So I want to implore that all of you spend a little bit of time looking at the night sky. And you might say, well, I live in a city. Don't tell me, I live in Chicago. We can mostly only see planes. However, you have a wonderful resource right nearby. I believe Giauga, I'm hopefully not screwing up the name. Thank you, I got a thumbs up from the front row. So this is a wonderful dark sky park that actually, when I moved to Chicago, I drove from New York City and I stopped off at, so official astronomer approved, I guess. So Geauga Park is just about an hour east of here, and it is one of many dark sky parks that exist in well, across the globe, but within the United States as well. It's the closest one to you, but there are others as well in Upper Michigan, for example, or over in central northern Pennsylvania. It's a very nice one called Cherry Springs. And so you can go to these places, which are essentially like dark sky preserves, and you can observe the night sky. Now, if you're only an hour outside of Cleveland, you might still see some of the glow of that city lights. But it is a very profound thing to go and experience the night sky in and of itself. Now, I love telescopes just as much as anyone, but it is an amazing thing to think that these stars, shared across centuries and millennia with other cultures, are the same ones that have informed much of what we know about astronomy in our world today. I was asked a wonderful question. One of the things that I love about working at the Adler Planetarium is that when people ask you questions about science, they often ask you questions in a way that your professional colleagues might not, and it makes you think about the topic differently. And so one day I was answering questions in the planetarium, and a gentleman raised his hand and he said, when you're looking out into space and light is traveling through space from some astronomical object to Earth, and it gets to Earth, does it stop? I thought, that's a funny question. And then I thought, well, yeah. So if you're out under a dark night sky and the light from those stars is falling on you and it's falling on the Earth, it's essentially those particles of light, photons, light waves, are landing on the Earth and being absorbed or reflected. And if you're actually seeing something with your eye, then it's traveling into your body where it hits your retina and creates an electrical signal in your brain. And then I thought, oh God, I have to leave and go be by myself for a minute and just think about that. So just in case you were wondering whether astronomers ever get freaked out by the universe, we do. But this is an amazing thing that light can travel to you from across the universe, because the universe does have an order and a structure, and it's something that those observations can help you discern. And so I highly recommend that you take part in this ancient tradition, but also that you not only look for the things that you can see, but the things that have been unseen so far. And with that, I'll invite you to come downstairs. There's a name of a room that I've been told multiple times. Follow the people in red coats and they will take you there. And come talk with me about your questions, because I'd love to know what you're thinking about and wondering about. And I'm so grateful to have the opportunity to speak with you all today. Thanks. Thank you.